Hello everyone, I am Nilofer Yasmin. This is Satellite and Radar System. We are talking about moving target indicator radar today. So first of all, what is a moving target indicator? We all know that radar is an acronym for radio detection and ranging. That is, radar is used for detection of a body and ranging, that is calculation of distance of that target from the transmitting unit. Radar specifically uses RF frequencies. Electromagnetic waves are transmitted and the reflected back echoes are analyzed, and by analyzing the property of waves and the time of travel, the distance could be calculated. Other parameters could also be calculated. What a radar cannot do is detect the color of the object. Apart from it, it can detect the presence, it can calculate the range, it can detect the velocity with which it is either approaching or moving away. In case of moving target indicator radar, this is specifically used to detect my moving targets and not the stationary one, right? So how it works? If a radar is used for detecting the movable target, then the radar should receive only the echo signals due to the movable target and not from the stationary ones. The echo signal is the desired one, right? The received signal. However, in practical applications, radar does receive the signals because of the presence of stationary objects in the vicinity as well. And those stationary objects which generate signal which are received by radar are called as clutters. This is a term which we'll be talking about more often, right? Echo signals because of the stationary objects like land and sea that could possibly generate so much of noise that could be misinterpreted as the signal received because of some target. So the radar has to wisely work. For this purpose, radar uses the principle of Doppler effect. Now, using Doppler effect will help me differentiate my stationary target from the moving target. So this is the concept on which, this is the phenomena which is used by my moving target indicator. My moving target indicator are based on, we can classify it based on the type of transmitter it uses. Either it could use power amplifier transmitter or it could use power oscillator transmitter, right? If my radar system uses single antenna for both transmission and reception, then it has to be enabled with a duplexer. That is a well-known truth. So let's see the block diagram of my MTI radar. My MTI radar consists of these many blocks. First of all, wave has to be generated. The electromagnetic wave which is used here is not of continuous type, it is of pulse type. So high frequency or high energy pulses are generated with the help of pulse modulator, which is first amplified with the help of power amplifier, then which is sent to duplexer, and in the transmission mode, my antenna acts to transmit my, it will act in receiver mode, reception mode, right? So the received frequency will go to mixer 2. Another input to mixer 2 or the product modulator is my locally generated frequency. So to the product modulator or mixer 2, the two frequencies given is the received echo signal and another is the locally generated signal. The difference frequency could be amplified with the help of IF amplifier. We know in reception and demodulation and detection what happens. A radar receiver acts like a basic super heterodyne receiver. So when it receives the signal, the RF frequency is first converted into IF range, then it is converted into baseband range in which originally it was transmitted. Then the IF frequency is amplified, and with the help of phase detection, which uses coherent oscillator and delay line canceller, are also helpful in removing the DC component which comes into the received signal, right? We have a mixer 1 here, which gets one of the input from the coherent oscillator, right? This generates frequency which is coherent in phase and frequency to the previous frequency, right? This input goes to my power amplifier. It helps, hence it acts on feedback and helps in maintaining the system with a good stability. Pulse modulator, it produces a pulse modulated signal and is applied to power amplifier. It amplifies the power level, right, of the pulse modulated signal. Local oscillator produces a signal having stable frequency FL. It is denoted by FL and it is called as stable local oscillator. It is also called as STELO in many books. The output of local oscillator is applied to both mixer 1 and 2. True. Now, coherent oscillator, here it produces a signal having an intermediate frequency FC. It generates FC, right? This signal is used as a reference signal. Here, my local oscillator frequency is used as a reference signal and output of it is applied to both mixer 1 and phase detector. You could see phase detector and it goes to mixer as well, right? Mixer 1 can produce either sum or difference of the frequency that are applied to it. The signals having frequencies of FL and FCs are applied to mixer 1, right? FL from here and FC from here. The two of the inputs to mixer 1 are FL and FC, right? Mixer 1 is used for producing the output which is having the frequency FL plus FC, right? The duplexer here is a microwave switch. It helps in switching the mode from transmitter to receiver, which connects the antenna to either the transmitter section or the receiver section based on the requirement. Here the antenna transmits the signal having frequency which is FL plus FC, right? When the duplexer connects the antenna to power amplifier, similarly antenna receives the signal having frequency FL plus FC plus minus FD. Here FD, this is the Doppler frequency. You know, FL plus FC, when it's transmitted at the time of reception, this frequency could be increased by value FD if the target is approaching, and if the target is leaving, that is going beyond, then this will be minus FD. So hence combining these two, we can rewrite this. Mixer 2 here can produce either sum or difference of the frequencies that are applied to it. So to mixer 2, one that is received is FL plus FC plus minus FD, another input is FL, right? So the sum and difference could be FL plus FC plus minus FD and FL. That this is one of the frequency which is applied. This is the received echo and this is the locally generated frequency. These are applied to mixer 2, right? I could write it here. This FL plus FC plus minus FD. One of the input, another input is FL, right? The IF amplifier will amplify the sum or the difference, right? The output could be either this, FL could be either subtracted or added in twice form, whereas IF frequency, as is the difference frequency, is lower than the RF frequency. Here mixer 2 will generate the difference frequency. Difference of these two frequencies will cancel out the FL term, and what do we get here is FC plus minus FD. So output of my mixer 2 is FC plus minus FD. This is usually my output of mixer 2, which goes as input to my IF amplifier, right? What is the role of phase detector? It is used to produce the output signal having frequency FD from the applied to input signals, which are having the frequencies of FC plus FD and FC. These are the frequencies. The output of phase detector can be connected to delay line canceller now. What will be the role of my delay line canceller? My delay line canceller usually helps in extracting the DC component, because the DC component will be because of the stationary objects in the vicinity. So that when we cancel out the received signal because of the stationary objects, we can accurately calculate the signal and analyze it because of the moving target. Right? Block diagram of MTI radar with power oscillator now looks like the same. The difference here is, instead of the amplifier, we replace it with a magnetron oscillator, right? So it will be same both the block diagram, whereas block corresponding to transmitter section will be different here. In transmitter section, instead of the amplifier, we replace it with a oscillator. Pulse modulator will be generating my frequency, right? And rest of the procedure, let's see. It uses single antenna for both transmission and reception. So we need to use a duplexer here, right? Output of magnetron oscillator and output of local oscillator here are applied to mixer 1. Magnetron oscillator output and local oscillator, right? And local oscillator output. These two are the inputs to my mixer 1, right? Output of mixer 1 is applied to coherent oscillator. Therefore, the phase of coherent oscillator output will be locked. Coherent oscillator here act in phase locked loop, right? Here the output of my coherent oscillator can be used as a reference signal, right? Which is always the case. It is used as a reference signal. Now next thing is the working remains same as what we have studied in the previous one, right? The only difference here we have is this block. Instead of amplifier, we do use an oscillator. Now let's study how my delay line canceller works and how does it help in MTI detection. My delay line cancellers are basically filters which eliminates the DC component of echo signals received from the stationary targets. So delay line cancellers are nothing but filters. What kind of filters? Which will remove my DC component. This eliminates the DC component of echo signal received from the stationary target. This means it allows AC component of my echo signals received from the non-stationary targets, that is moving targets, right? We may use two kinds of delay line canceller based on their structure, right? Delay line canceller can be classified into the following two types. The types are my single delay line canceller and double delay line canceller. Let's see how it works. What is a delay line canceller? Combination of a delay line and a subtractor is called as my delay line canceller. It is also called it is also called as the addition of delay line and the subtractor, right? So here, after receiving the RF signal from the radar wave, it first goes into the delay line so that we can compare the received input with the reference signal, that is the previously received pulse, right? So this delay line will help me compare my received input with the previous pulse, and with the help of the subtractor, if we receive some difference, then that difference with the help of full wave rectifier, we know full wave rectifier will act in removing my DC component, right? So the signal received because of the clutter, background noise or stationary objects in the vicinity can be removed with the help of my single delay line canceller. Why the name single delay line canceller? Because if the same arrangement is repeated twice, then that is called as double delay line canceller. The output of subtractor here is applied as input to the full wave rectifier. Therefore, the output of full wave rectifier looks like as shown in the following figure. It is nothing but the frequency response of my single delay line canceller, right? This is how output, we know output of full wave rectifier, how does it look like? On the x-axis, if we do have frequency, and on the y-axis, if I have amplitude, this is how my output of full wave rectifier looks like. So this diagram represents the frequency response of my single delay line canceller. If I talk about my double delay line canceller, then if I have this arrangement in concatenated manner, that is, if a single delay line canceller is concatenated one after another, then we do call it as double delay line canceller. We know that a single delay line canceller consists of a delay line and a subtractor. If two such delay line cancellers are cascaded together, then it is called as double delay line canceller. So it will have better frequency response. But we do face some issues in delay line cancellers as well. They are not capable of removing completely my DC components. And what is the reason behind this thing? Why are not they capable of removing my DC components fully? This is because of a phenomena which is called as blind speed. Now, what is blind speed? We know that response of a single delay line canceller will be 0 whenever the argument in the amplitude factor, argument, that is angular argument of a wave, in the amplitude factor of V equals to V1 minus V2 equals to this is 0. As this is sine of this, so it is 0 at what points? When the angle is either 0 or pi or integer multiple of pi. When this is 0, the response, that is the difference, completely becomes 0. And when it gives no response, that is the blind point, right? Here, if any target is moving, these are the points. Here, if any target appears, then my radar is not capable of detecting those targets. These are my blind speeds. And where do I obtain these blind speeds? At angle 0, at angle pi, at 2 pi, 3 pi, at every integer multiple of pi, right? So when response of my delay line canceller is 0, that is the point. If some target is approaching us or moving away, we are not able to identify it. So that difference is because of the blind speed, right? When n equals to 0, 1, 2, then fp is up to fp. Here fp is my pulse repetition frequency, that n equals to 0, 1, 2 up to any point. Here in this equation, my fp is pulse repetition frequency, that is inverse of the time duration of repetition of pulse, right? The delay line canceller not only eliminates the DC component caused by the clutter, but unfortunately it also rejects any moving target whose Doppler frequency happens to be same as PRF or multiple of them. So that is another problem. Not only at these angles, but also if the Doppler frequency happens to be same as that of pulse repetition frequency, then also this could not be detected, right? So these are some limitations of my MTI moving target indicator. In spite of using delay line cancellers also, there are still some targets which cannot be detected if the pulse repetition frequency becomes equal to that of my FT or at these angular points, right? Those relative target velocity which result in zero MTI response are called as blind speeds. So what is basically my blind speed? When the relative target velocities which results into zero MTI, right? So these are at these points where Vn is the nth blind speed. So how a blind speed could be given? This is a velocity given a V underscore n equals to n pi by 2t, which is equals to n pi fp by 2. Fp here is my pulse repetition frequency, lambda is the wavelength of the frequency signal which is used. Vn is my nth blind speed. If lambda is measured in meters, then fp in hertz and the relative velocity in knots. The blind speed is given by this. This is one of the major limitation. This is one of the major limitation of my pulse MTI radar. These are present in pulse radar because Doppler is measured by discrete samples, pulses at PRF rather than continuously. So reason behind it is using pulses. If instead of pulses, if we would have used continuous wave, then this problem could have been diminished. What is multiple or staggered pulse? What is the remedy of overcoming this blind speed? We can use multiple or staggered pulse repetition frequency. Now, what do we mean by multiple or staggered pulse limitation frequency? If we keep changing my pulse repetition frequency, right? We don't keep the pulse repetition frequency constant. Now, we can change it at different moment. So, using multiple pulse repetition frequency is a solution to it, right? And what is staggered pulse repetition frequency? Let's study. If radar is operating at multiple PRF or its PRF is changed either pulse to pulse or scan to scan, then effect of blind speed can be eliminated. True. If two radars operating at same frequencies but having its difference, a pulse repetition frequency, then if one radar is blind to moving the target. True. So if we use a single radar but with different PRF, then same effect could be achieved, right? Instead of using two different radars operating at two different frequency, let's have a single radar and operate it at one frequency. After some time, change its pulse repetition frequency, or at every pulse change. If we keep changing it every pulse, that will be called as staggering. This process is called as staggering. Staggering of pulse repetition frequency is generally employed. It's a famous technique in air traffic control radar, such as surveillance radar element, right? Frequency response of pulse repetition frequency. See, this has different frequency, this pulse, this has different frequency. There are hardly any point where the energy goes to 0, right? So, one case was this, where here we were receiving blind speeds. Here, one is this velocity, another is, one is this frequency, another is this frequency. So, we hardly get some point where the amplitude becomes 0 at any particular frequency. So, using staggering the pulse repetition frequency will eliminate my blind speed. So, we can change the pulse repetition frequency pulse to pulse, which is known as staggered PRF, or we can change it scan to scan or dwell to dwell. The problem occurs in using staggered PRF is the residual of unconcealed echoes. There are still some problems which could be ruled out. So to minimize the second time around echoes, what are second time around echoes? When I transmit a pulse from the transmitting antenna, I receive the echo back. If I receive the echo back after transmitting the second pulse, that is exceeding the maximum ambiguous range, then that is second time around echo, right? So this is still a problem which could be minimized. Right? Second time around echoes. To minimize the second time around echoes, we use unstaggered PRF in sector where second time around are expected more, right? Where target is considered to be at a very large distance. So there are certain terms like what is subclutter visibility. Subclutter visibility may be defined as the ability of MTI radar to detect the moving target, right? So it defines the performance of an MTI radar. It is equal to the gain in signal to clutter power ratio, right? Cancellation ratio. What is cancellation ratio? It is the ratio of fixed target signal voltage after MTI cancellation to signal voltage without MTI cancellation, right? It may be defined as ratio of these two things. It is a number which is always less than 1 and may be expressed in decibel, right? What is target visibility factor? It is the ratio of signal strength from target which is moving at a specified radial velocity to signal strength from the same target when it is moving at optimum radial velocity. Like in case of antenna engineering also, we do it, right? For directional antenna and the isotropic antenna, like that. So these are certain terms which we should know about radar. These are the references I've used. Thank you.